My name is Boan. I'm from Singapore. I'm going to talk about, I mainly work on computational game theory for security. So today I'm going to talk about our work on applying computational game theory to help the government to make big decisions. This is joint work with a master student, Jerry Gan, and PhD student, Xiong. So urbanization is a trend, especially in Asian countries like China, and it leads to many issues such as transportation, energy, water treatment, lots of issues. For all these scenarios, the government needs to make decisions such as lots of policies, and there is always conflict between individuals' interest and the social welfare. So in those scenarios, people are always involved. As we know, people in most cases, they're kind of self-interested. They will make their decision which is best for them, but the government, they want to make good policy which is the best for the whole society. So that's equilibrium. We know that for most games, equilibrium may not be social optimal. So we look at those type of problems and apply game theory to model those games and try to compute the optimal policy for the government. We work on two problems. First one is optimal pricing for taxi systems, and the second one is planning and pricing for EV charging station, which is somehow unique to your talk, but we look at different aspects of this problem. So I will go through these two problems one by one, and I will ignore all the technical details so you can go to our paper or talk to me. I have a poster outside during the poster session. So the first problem is about optimal pricing for taxi systems. So we all know that taxis everywhere, many cities, and so I'm now in Singapore. Before I went to Singapore, I spent 1 year in Beijing, and after I started working in Beijing, one problem I observed is during peak hour, like the morning or the evening, like maybe 5 p.m., it's almost impossible to get the taxi. Even you see empty taxis, they will not work. They will not. What's happening is there's huge demand, but there is no supply during rush hour. Then I start to, every time when I took a taxi, I start to talk to the drivers and what's going on, why is this? It turns out, so here there are two, like rush hour, lots of people are waiting to take a taxi, but at the same time, we can see lots of taxis are parking at huge parking lot or along the street. Drivers just to talk to each other, they will not choose to work. So what's the reason? Turns out rush hour, the traffic congestion is terrible in Beijing, and the pricing scheme is, most time it's almost based on the distance. Because they cannot move fast, they basically need to lose money, because when you start, stop, the gas consumption is even higher. So the simple idea is we might increase the price during peak hours. It's very simple, and it's been used in like cities in Singapore. But the problem here is we try to analyze how much can we increase. What's the optimal price for rush hour, for instance, to improve the efficiency of the taxi systems. So that's the problem we look at. So we try to adjust the fair price to maximize system efficiency. This is very challenging because taxi system is extremely complicated. There are many factors with complex interdependency, like customer demand, congestion level, transport speed, customer waiting time. All those factors, they're kind of interdependent. And also there are time variances, like peak time, non-peak time, very complicated. And also taxi drivers, they're kind of strategic. They're playing some kind of game. They're profit driven. They also have lots of scheduling constraints. For instance, they cannot work for 2 now. So first we have to model this problem. So there are many factors. I will ignore the details. For instance, we have to look at fair price. Two very important factors, fair price and also how many taxi drivers are working on the street will affect many other factors such as drivers' utility, road condition, because more taxis are working, then the congestion will be higher. Travel speed and waiting time of customer, that will also have an impact on the demand of customer and also system efficiency. It's very complicated. And in the end, we find that if we assume that taxi driver, they will make some decision, we can replace this part. Taxi driver strategy will depends on the fare price, and also it will determine how many taxis will work. So we build this model, and it's a complicated model. So those equations, everything is from transportation science. We just borrow those equations and build the model. Then we try to analyze the problem, try to compute the optimal pricing for a taxi market. So let me talk a little bit more about the taxi driver strategy. So here we basically say that it's a schedule. It's a 0, 1 vector. For instance, we can treat each period as like 1 hour. So 0 means it's not working, 1 means it's working. And they also have some constraints. For instance, they cannot work for continuous for more than 4 hours, for instance. Also, they cannot, every day, they cannot work for more than 10 hours, those type of constraints. So we model that. We formulate this as a Bilevel optimization problem. We're trying, the government first decided the pricing for the taxi market, and then each taxi driver try to compute the optimal strategy. So I guess here we have to solve not just scale problem, because the strategy space of a taxi driver will exponentially increase the number of periods. So we have to find out efficient algorithm. So there are a couple of solution approaches. I guess for this one key idea we use here is, instead of compute the mixed strategy for the taxi driver, we compute the probability of this something called n-term schedule, and the size of the n-term schedule is much smaller than the size of the original schedule. So we compute that, and we're able to prove that based on optimal probability of n-term schedule, we can compute an equivalent mixed strategy. So we can guarantee optimality. So and later we come up a much more efficient algorithm, which is based on the idea of different representation of polytope. Vertex representation is complexity much higher, and also the half space representation, the complexity, the space complexity is much smaller. So and also we develop an algorithm to solve more general cases in which taxi drivers face other type of constraints. For instance, in lots of cities in China, the governments issue policies such as, if you work at 4 p.m., you have to continue to work for another 3 hours, because lots of taxi drivers that do not choose to work, just find other excuse such as they need to switch, those types of things. So we are able to find out the optimal strategy to handle arbitrary constraints. So let me talk about another problem, about EV charging problem. I found this problem after I moved to Singapore. Singapore government is trying to introduce more EV in the future. I guess maybe last week they signed a big contract with one company in China. They try to introduce maybe thousands of EVs to Singapore. So EV is good, but if you charge at home, we need much longer time. Yes, I will quickly go through this. But if we have this charging station, it's much faster. So we have to, government has to decide where to put EV charging station. This is still a Bilevel optimization problem, because after governments decide where to put EVs, then the drivers will play some kind of congestion game. They will decide where to charge based on many parameters. And then we have a model to model this problem, model the strategy of those drivers, EVs, and then come up efficient algorithm to solve this nonlinear program with infinite number of constraints. I will ignore the details. We have papers for this, and this year we work on another problem, whether we can play with pricing to improve the traffic congestion and improve the comfort of those EV drivers. So the final point I want to make is, for lots of problems, like big cities, when human beings are involved, game theory can be useful because people are normally not follow the policy, or they might be self-interested. Maybe we need to combine game theory with human behavior modeling, and there are many application domains. Thank you.
So it wasn't clear to me, how is the efficiency of the taxi system defined? Is it
So this is the number of served customers. The number of served customers.
And if you define taxi efficiently differently, like CO2 produced or...
Yeah, you can do that. Well, I guess it might be the same in terms of the difficulty of solving that problem.
Okay. All right, well, thank you.
You have one more question?
Oh yeah, I'm just curious. The lack of taxis during rush hour might be an objective of the government as well. Since it's congestion, they don't want to put more cars on the road.
I did not mention that. So the government, and this for the Beijing government, they have enough taxis. So for non-peak hours, there are lots of taxis work on roads. They cannot find a customer, but they're not that smart in that sense. So the government needs to regulate to improve the efficiency.
Yeah, I think they both go to how you define the efficiency. But anyways, thank you very much.